Quantum physics shattered our classical understanding of the universe. Once, we believed reality was solid, predictable, and governed by cause and effect, but the quantum world revealed something far stranger. At the subatomic level, particles behave both as waves and as matter, existing in multiple states at once until they are observed. This phenomenon, known as superposition, defies common sense and challenges the idea of an independent, objective reality. When physicists like Planck, Einstein, Bohr, and Schrödinger explored these mysteries, they discovered that the simple act of measurement appears to influence what actually happens. Before observation, a particle is a cloud of possibilities. After observation, it becomes a concrete event. This means reality might not be something that simply is, but something that emerges through interaction, awareness, and observation. The deeper scientists looked, the more they realized that uncertainty, not certainty, lies at the foundation of existence. Quantum physics doesn't just describe how matter behaves, it forces us to question what reality truly is and whether consciousness itself might be the missing link between potential and manifestation. It is here, in this strange intersection of mind and matter, that the quantum mystery truly begins. The dawn of the 20th century marked one of the most dramatic shifts in human understanding, the quantum revolution. For centuries, science had been guided by the elegant laws of classical physics, built by Newton, Maxwell, and others. In this worldview, the universe functioned like a perfectly designed clock, predictable, mechanical, and governed by cause and effect. Every event had a clear reason, every particle a precise location, and the future could, in principle, be calculated from the past. But cracks began to appear in this solid framework. In 1900, Max Planck, while studying how hot objects emit light, made a strange discovery. He found that energy wasn't emitted continuously, as everyone believed, but in discrete packets he called quanta. This was the first hint that the universe might not be as smooth and continuous as it seemed. A few years later, Albert Einstein expanded on this idea to explain the photoelectric effect, how light can knock electrons off a metal surface. His conclusion was shocking. Light behaves not only as a wave but also as a stream of particles or photons. This revelation earned him a Nobel Prize and opened the door to a new reality, one where energy, light, and matter could act both as waves and particles depending on how we observe them. The mystery deepened in the 1920s when Niels Bohr, Werner Heisenberg, and Erwin Schrödinger developed the formal structure of quantum mechanics. Their equations described the behavior of electrons not as particles orbiting a nucleus like tiny planets, but as probability waves, fields of potential that only become definite when measured. Heisenberg's uncertainty principle soon revealed another truth. It's impossible to know both the position and momentum of a particle with complete precision. The more accurately we know one, the less we can know the other. This shattered the notion of absolute determinism and introduced fundamental uncertainty into the heart of physics. Meanwhile, Schrödinger's wave equation described how these probability waves evolve over time, suggesting that reality itself exists as a field of possibilities. Only upon observation do these possibilities collapse into a single outcome, a process that remains one of science's greatest enigmas. This was not just a scientific revolution, it was a philosophical one. The observer was no longer separate from the observed. Human consciousness, or at least the act of measurement, seemed to play a role in defining what is real. Einstein resisted this idea, famously declaring, "God does not play dice with the universe." But experiments would continue to prove that, at the quantum level, nature does behave probabilistically. The quantum revolution fundamentally transformed how we view the universe. It revealed that beneath the solid world of matter lies an invisible ocean of energy, vibration, and potential, a realm where reality is not fixed, but fluid, responsive, and interconnected. And from that moment on, science and philosophy would never be the same again. Few scientific experiments have challenged our understanding of reality as profoundly as the double-slit experiment. Simple in design yet staggering in implication, it reveals that at the quantum level, the act of observation itself can alter the outcome of events. Imagine firing tiny particles like electrons or photons at a barrier with two narrow slits, with a screen behind it to record where they land. If only one slit is open, the particles form a pattern directly behind that slit, just as we'd expect from solid objects. But when both slits are open, something extraordinary happens. Instead of forming two clusters, the particles create an interference pattern, a series of light and dark bands resembling the ripples made by overlapping waves. This pattern suggests that each individual particle doesn't just pass through one slit or the other, it somehow passes through both at the same time, behaving like a wave of probability that interferes with itself. Each particle seems to explore all possible paths simultaneously until it hits the screen, where it finally appears as a single dot. Here's where the mystery deepens. When scientists try to determine which slit each particle actually goes through, by placing a detector near the slits, the interference pattern disappears. The particles suddenly behave like solid bullets, going through one slit or the other, never both. The mere act of measuring changes their behavior. It's as though the particle knows it's being observed and instantly adjusts itself to behave differently. Without observation, it acts as a wave of infinite possibilities. With observation, it collapses into a single outcome. This strange effect, known as the observer effect, is not a trick of instrumentation but a genuine feature of quantum mechanics. Repeated countless times with electrons, atoms, and even large molecules, the results remain the same. Observation determines what reality becomes. So what does this mean? At its core, the double-slit experiment suggests that reality is not fully formed until it is observed. Before measurement, a quantum object exists in a superposition, a cloud of probabilities describing all possible states. Once observed, the wave function collapses, and one outcome becomes real. The implications are staggering. Does this mean consciousness directly influences reality? Some physicists like John von Neumann and Eugene Wigner believed so, arguing that the observer's awareness is the final step that brings potential into existence. Others claim that the measuring device itself causes the collapse, without invoking consciousness at all. Regardless of interpretation, the double-slit experiment forces us to question our assumptions about the nature of existence. Reality, it seems, is not simply out there waiting to be discovered. Instead, it may be participatory, shaped by the act of observation, interaction, and awareness. In this simple experiment lies one of the most profound messages in all of science: that the universe is not a passive stage, but a living, dynamic interplay between the observer and the observed, a mystery that continues to blur the line between physics and philosophy. The observer effect is one of the most misunderstood and debated ideas in quantum physics. It describes how the very act of measuring or observing a quantum system appears to change its behavior. In everyday life, observation seems passive. You can look at a tree without altering its leaves or roots. But in the quantum realm, the situation is entirely different. When we observe a particle, we don't simply see it, we fundamentally affect what it becomes. In experiments like the double-slit experiment, unobserved particles behave like waves, existing in a state of superposition, multiple possibilities at once. Yet, when a measurement is made, the wave collapses, and the particle takes on a definite form. This suggests that observation changes reality. But what exactly is meant by observation? Here lies the core of the debate. Some early quantum pioneers, including John von Neumann and Eugene Wigner, proposed that consciousness itself causes the wave function to collapse. According to this view, the universe remains in a haze of probabilities until a conscious observer interacts with it, implying that the mind plays a direct role in shaping physical reality. This interpretation bridges science with mysticism, echoing ancient spiritual teachings that reality arises from awareness. However, most modern physicists interpret the observer effect differently. In their view, Observation doesn't necessarily mean a human mind watching. It refers to any interaction between a quantum system and its environment. When a particle collides with a detector, photon, or molecule, the system's wave function interacts with the surroundings, effectively collapsing into one outcome. This is explained by decoherence theory, which removes the need for consciousness as a physical cause. Still, even this mechanistic view cannot escape philosophical implications. If all measurements ultimately result in definite outcomes only when information is exchanged, then the concept of the observer becomes inseparable from the idea of knowledge or awareness. Reality may not depend on human consciousness per se, but it still depends on information being registered somewhere in the fabric of existence. The observer effect thus occupies a fascinating space between science and mysticism. To physicists, it highlights the limits of objective measurement and the intertwined relationship between observer and observed. To philosophers and spiritual thinkers, it suggests that the universe is participatory, that consciousness, or at least awareness, is fundamental, not secondary. The tension between these perspectives continues today. Is consciousness an active creator of reality, or merely a witness to quantum interactions? Science hasn't resolved this question, but the very fact that it arises shows how deeply quantum mechanics blurs the line between physics and philosophy. Perhaps both views hold truth. Observation, whether through human awareness or universal interaction, appears to be the bridge between potential and actuality. The observer effect reminds us that we are not isolated spectators of a fixed world. We are participants in an unfolding quantum dance, where mind and matter are far more connected than we ever imagined. In 1935, Austrian physicist Erwin Schrödinger introduced a now-famous thought experiment to illustrate the absurdity and mystery at the heart of quantum mechanics. Known as Schrödinger's cat, it presents a paradox that forces us to question what it truly means for something to exist. Imagine a cat sealed inside a box with a small vial of poison, a Geiger counter, and a piece of radioactive material. The setup is designed so that within 1 hour, there's a 50% chance the radioactive atom will decay and trigger the release of the poison, killing the cat, and a 50% chance that it won't decay, leaving the cat alive. According to quantum theory, before the box is opened, the atom exists in a superposition, both decayed and undecayed at the same time. If the atom is both decayed and not decayed, then, by extension, the cat must be both alive and dead simultaneously. Only when an observer opens the box and looks inside does the wave of probability collapse into one definite reality, either a living cat or a dead one. Until that moment, the cat exists in a strange twilight state between life and death, a paradox that defies logic. Schrödinger proposed this scenario not to suggest that cats actually exist in two states at once, but to highlight the strangeness of applying quantum principles to the macroscopic world. Quantum mechanics works perfectly for atoms and subatomic particles, but what happens when those same rules are scaled up to everyday objects? The thought experiment exposes a profound problem known as the measurement problem. When and how does potential reality become actual reality? Some interpretations, like the Copenhagen interpretation, claim that observation itself, whether by a conscious mind or a measuring instrument, causes the collapse of possibilities into a single outcome. Others, such as the many worlds interpretation, take a more radical approach. The universe splits into parallel realities at the moment of observation, one where the cat lives and another where it dies. Both outcomes occur, but in separate, coexisting worlds that never interact. The paradox of Schrödinger's cat goes far beyond physics. It challenges our understanding of existence, consciousness, and reality itself. If observation is required to determine what is real, then what was the state of the universe before any observers existed? Does reality depend on consciousness, or does it unfold automatically through interactions at the quantum level? The cat-in-the-box scenario forces us to confront an uncomfortable truth. Reality may not be absolute. It may depend on context, observation, and interaction. In the quantum world, things don't have definite properties until they are observed, suggesting that existence is a dynamic process not a static condition. Schrödinger's cat remains a powerful metaphor for the paradox of existence itself. It reminds us that the line between potential and actuality, life and death, matter and mind, is far thinner than we imagine, and that the very act of knowing may be what brings the universe into being. The idea that consciousness and quantum physics are intimately linked has given rise to a group of models collectively known as quantum mind theories. These theories attempt to explain how the mysterious, non-local, and probabilistic nature of the quantum world could give rise to or be influenced by conscious experience. They stand at the crossroads of physics, neuroscience, and philosophy, seeking to bridge the gap between matter and mind that classical science has struggled to close. One of the most well-known models comes from physicists Sir Roger Penrose and anesthesiologist Stuart Hameroff, who proposed the orchestrated objective reduction orchestroir theory. According to this model, consciousness arises from quantum processes inside microtubules, tiny structural components within the brain's neurons. Penrose argued that quantum states collapse not through random measurement, but through a fundamental, objective process tied to the structure of spacetime itself. When these collapses occur in the microtubules, they produce moments of conscious awareness. In essence, our thoughts and perceptions emerge from quantum events happening deep within the architecture of the brain. This theory attempts to answer a question that has long puzzled philosophers and scientists. How does subjective experience, our inner sense of being, arise from physical processes? Traditional neuroscience has struggled to explain the hard problem of consciousness, as coined by philosopher David Chalmers. Quantum mind theories suggest that the answer may not lie in classical chemistry or neural networks alone, but in the quantum realm, where particles can exist in superposition, become entangled, and behave in ways that defy logic. Another intriguing idea is the quantum consciousness hypothesis, which proposes that the brain acts as a kind of quantum computer. Instead of processing information linearly like a digital machine, the mind could exploit quantum effects, allowing for parallel processing, intuition, creativity, and non-local awareness. This could explain phenomena like sudden insights, telepathic experiences, or the interconnectedness described in mystical traditions. Supporters of these ideas argue that consciousness displays quantum-like properties. It is non-local, awareness is not bound by space. Holistic, the whole is greater than the sum of its parts, and unpredictable, like the collapse of a wave function. They suggest that the strange laws governing particles might also apply, in some form, to the mind itself. Skeptics, however, point out that the brain is warm and noisy, conditions typically hostile to delicate quantum states, which are easily disrupted. Yet, research in quantum biology has shown that quantum effects can indeed occur in living systems, such as photosynthesis, bird navigation, and even smell detection. These discoveries hint that the brain might have evolved mechanisms to maintain coherence long enough for quantum processing to play a role in cognition. Quantum mind theories do not yet offer definitive proof, but they invite us to view consciousness as something woven into the very fabric of the universe, rather than as an accidental byproduct of biology. If true, it would mean that mind and matter are two expressions of the same underlying quantum field, a reality where awareness is both the observer and the observed. The intersection of quantum physics and consciousness is one of the most intriguing yet misunderstood frontiers in modern thought. While genuine scientific inquiry into quantum phenomena and their philosophical implications has yielded profound insights, it has also opened the door to misinterpretation and pseudoscience. The mysterious language of quantum mechanics, wave functions, entanglement, collapse, and observer effect has often been borrowed by spiritual movements and self-help philosophies to justify ideas that have little to do with actual physics. At its core, quantum mechanics describes the behavior of subatomic particles, entities so small and elusive that they operate in a realm far removed from everyday experience. When physicists discovered that observation could influence experimental outcomes, it was a revelation about the limits of measurement, not necessarily about human thought altering the cosmos at will. However, this nuance is often lost in popular interpretations that claim you can manifest reality with your mind, or quantum physics proves we create our own universe. These ideas, though inspiring on a psychological or metaphysical level, oversimplify and distort quantum theory. The observer in quantum physics does not necessarily mean a conscious human being. It refers to any interaction that causes a quantum system to collapse into a definite state, whether by a detector, photon, or measurement device. Scientists like Richard Feynman and Stephen Hawking warned against conflating this technical concept with human consciousness or intention. To do so, they argued, is to drift from physics into metaphysics without clear evidence. Nevertheless, this misunderstanding persists, particularly within the New Age and law of attraction communities, where quantum has become a buzzword used to add scientific credibility to spiritual beliefs. While these teachings often promote positive thinking, empowerment, and mindfulness, invoking quantum mechanics as proof can mislead followers into believing that wishful thinking alone can manipulate physical reality. This not only trivializes the profound mysteries of physics, but can also encourage magical thinking, an overestimation of the mind's control over external events. That said, dismissing all spiritual interpretations as pseudoscience would also be short-sighted. Many mystics, philosophers, and even some physicists argue that quantum mechanics does hint at a deeper interconnectedness, a universe where separation is an illusion. This is not proof that thought directly shapes matter, but it does suggest that reality may be participatory and relational, not purely mechanical. In this sense, science and spirituality might be gazing at the same truth from different vantage points. The key, then, is discernment. True understanding lies in balance. Embracing the awe and mystery quantum physics reveals without leaping into unfounded conclusions. Science seeks evidence, while spirituality seeks meaning. When the two collaborate with respect rather than confusion, they can inspire both rigorous inquiry and profound insight. Quantum physics challenges us to rethink reality, but it does not hand us the power to bend it to our whims. To honor its depth, we must approach it not as a shortcut to spiritual certainty, but as a doorway to humility, wonder, and deeper questions about the nature of existence itself. Quantum mechanics, despite being the most successful and experimentally verified theory in physics, remains one of the most philosophically perplexing. The equations work flawlessly, but what they mean about reality is still debated. Over the past century, scientists and philosophers have proposed various interpretations of quantum theory, each offering a different picture of how the universe truly operates. These interpretations don't disagree on the math. They disagree on what the math tells us about existence itself. The most traditional explanation is the Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg in the 1920s. It asserts that quantum particles don't possess definite properties until they are observed or measured. In other words, the act of measurement causes the wave function, which represents all possible states, to collapse into a single, concrete outcome. Before observation, reality exists only as probabilities, not physical facts. Bohr famously summarized it, "There is no quantum world. There is only an abstract quantum description." This interpretation puts the observer at the center of quantum phenomena, blurring the line between objectivity and perception. However, many found the Copenhagen view unsatisfying, prompting the birth of competing theories. One major contender is the many worlds interpretation, proposed by Hugh Everett III in 1957. It suggests that the wave function never collapses. Instead, every possible outcome of every quantum event actually happens, but in separate, branching universes. When you measure an electron spin, for example, one version of you sees it spin up while another version of you, living in a parallel universe, sees it spin down. Reality in this model continuously splits into infinite versions, forming a vast multiverse of possibilities. Another fascinating idea is the pilot wave theory, or Bohmian mechanics, developed by Louis de Broglie and later refined by David Bohm. This interpretation restores determinism to quantum physics, proposing that particles have definite positions guided by a pilot wave that determines their motion. Unlike Copenhagen's randomness, Bohm's model implies an underlying order, a hidden reality beneath the apparent chaos, what Bohm called the implicate order. Some see this as a bridge between consciousness and physics, suggesting that the universe operates through a holistic, interconnected field. The objective collapse theories, like Penrose's orchestrated objective reduction, orchestroar, propose that wave function collapse is a real, physical process, not just a mathematical one. According to this view, when quantum superpositions reach a certain level of complexity or energy, they spontaneously collapse, producing a definite outcome. This could even be tied to conscious awareness, merging physics with the study of mind. Then there's the relational interpretation, which argues that quantum properties exist only in relation to the observer or system measuring them, meaning reality itself is not absolute but relational and contextual. Each interpretation paints a radically different picture of the cosmos: random, deterministic, infinite, or participatory. Yet none has been definitively proven or disproven. What they reveal is that reality may be far stranger and more fluid than our classical intuitions allow. The diversity of these theories reminds us that quantum mechanics doesn't just describe the universe. It questions the very meaning of reality itself. Whether consciousness plays a role or not, quantum interpretations collectively show that the world we perceive might only be one thin layer of a far deeper, more mysterious existence. Among the most striking and mystifying phenomena in quantum physics is quantum entanglement, a phenomenon Albert Einstein famously called spooky action at a distance. Entanglement occurs when two or more particles become linked in such a way that their properties are instantly correlated, regardless of the distance separating them. Measure one particle and the other knows immediately what measurement was made, even if it is light years away. This defies classical notions of space, time, and causality, and suggests that at the deepest levels, the universe is non-local and interconnected. Entanglement was first proposed theoretically by Einstein, Boris Podolsky, and Nathan Rosen in 1935, in the famous EPR paradox, which questioned whether quantum mechanics could provide a complete description of reality. They were troubled by the idea that measuring one particle could instantaneously affect another, seemingly violating the speed limit set by relativity. However, decades of experiments, most notably those by Alain Aspect in the 1980s, confirmed entanglement as a real physical phenomenon, not just a mathematical quirk. The implications of entanglement extend far beyond physics. At the quantum level, particles do not exist as isolated entities but as interdependent components of a larger, unified system. When one particle changes state, the other adapts immediately, as if all parts of the universe are communicating through an unseen web. Some scientists and philosophers suggest that this web hints at a fundamental connectedness underlying all reality, where the distinctions between self and other, observer and observed, are more fluid than classical physics suggests. This concept resonates with ancient mystical traditions that describe the universe as a living, interconnected whole. In Vedantic philosophy, everything arises from the same infinite consciousness. In Buddhism, all phenomena are interdependent and inseparable. In Hermeticism, as above, so below, as within, so without. Quantum entanglement offers a scientific metaphor for these teachings, suggesting that the cosmos is not a collection of isolated objects, but a vast network of relationships. Entanglement also has practical applications, particularly in quantum information science. It underpins quantum computing, where entangled qubits perform computations simultaneously, and quantum cryptography, which enables ultra-secure communication. These technologies are not just demonstrations of physics. They are glimpses into a universe where information and connection may be as fundamental as matter and energy. Some theorists take this further, suggesting that consciousness itself may operate in a similarly non-local and entangled way. If particles can remain connected across vast distances, could awareness also be an emergent property of a cosmic web of mind? While speculative, such ideas hint at a universe where mind and matter, self and cosmos, are interwoven in a single dynamic fabric. Quantum entanglement challenges us to reconsider our deepest assumptions. It suggests that the universe is not merely a collection of isolated parts, but an intricate web of oneness, where every particle, system, and observer is connected in profound ways. At the quantum level, the boundaries we take for granted, between here and there, self and other, potential and actual, begin to dissolve, revealing a universe far stranger, richer, and more unified than we ever imagined. One of the most profound concepts emerging from modern physics is the idea that the universe is not a collection of isolated particles, but a vast, dynamic quantum field. According to quantum field theory, every particle, electron, photon, quark, is actually an excitation or vibration of an underlying field that permeates all of space. Particles are not fundamental. They are temporary manifestations of deeper energy patterns. This insight challenges the classical notion of a solid, objective reality and opens the door to understanding the universe as vibrational, interconnected, and information-based. In a quantum field, reality is a continuous interplay of potential and actualization. Before measurement, particles exist as clouds of probability, potential states rippling across the field. Observation collapses these probabilities into definite outcomes, revealing the intimate link between the observer and the fabric of reality. This dynamic suggests that the universe is less like a static machine and more like a living, responsive matrix of energy and information. Building on this concept, some physicists and cosmologists propose the idea of a holographic universe. A hologram is a two-dimensional surface that contains all the information needed to project a three-dimensional image. Applied to the cosmos, this suggests that the three-dimensional reality we experience may emerge from information encoded on a distant, lower-dimensional boundary, such as the edges of the universe. Pioneering work by physicists like David Bohm and later Juan Meldacena hints that the universe may be informational at its core, with matter and space-time emerging from deeper quantum processes. The holographic model provides an elegant explanation for phenomena that classical physics struggles to address. It aligns with the idea that every part of the universe contains information about the whole, a principle that resonates with mysticism, ancient philosophy, and even consciousness studies. If reality is fundamentally informational, then mind, observation, and awareness may not merely reside within the universe. They could be an integral part of its structure. Quantum fields and the holographic principle also offer a fresh perspective on the interconnectedness of all things. Entanglement, superposition, and non-locality, previously mysterious, can be seen as natural consequences of a universe encoded in information rather than solid matter. The behavior of particles is not random but reflects a cosmic intelligence woven into the quantum field, where the whole and the part are inseparably linked. This view blurs the lines between science and spirituality. Ancient wisdom often described the universe as a vibrational and interconnected whole, where consciousness and reality co-create one another. Modern physics now provides a framework in which these insights may not be purely metaphorical. They may reflect the fundamental architecture of existence. The quantum field and the holographic universe suggest that reality is a living tapestry of energy, information, and potential, where matter is emergent, consciousness is participatory, and every part reflects the whole. It is a universe that is far stranger, more subtle, and more profound than our everyday perception allows, inviting us to reconsider what is real, what is possible, and what role we play as observers within this vast cosmic web. The question of whether consciousness interacts with quantum systems has long fascinated scientists, philosophers, and mystics alike. While much of the discussion remains theoretical, a growing body of experiments suggests that the observer may play a more active role in shaping quantum outcomes than classical physics would predict. One of the earliest hints came from the Double-Slit Experiment, where electrons or photons fired at a barrier with two slits create an interference pattern when unobserved, behaving like waves. When a detector is placed to measure which slit a particle passes through, the interference disappears, and the particle behaves like a solid, localized object. This experiment, repeated countless times, demonstrates that measurement, not just mechanical interaction, affects quantum outcomes. While the observer need not be human, the results raise questions about whether consciousness or awareness is integral to the process of collapsing possibilities into reality. In the 1970s and 1980s, researchers such as Dean Radin and the Princeton Engineering Anomalies Research (PAIR) lab conducted experiments with random event generators, REGs. These devices produce outcomes that are statistically random, such as flipping virtual coins at extremely high speeds. Participants were asked to influence the devices using intention or focused thought. Over thousands of trials, small but statistically significant deviations from chance were observed, suggesting that human intention could correlate with quantum-level events. Critics argue that these effects are weak and prone to experimental error, but the studies remain a provocative window into potential mind-matter interaction. Other studies explore quantum coherence in biological systems, such as photosynthesis, bird navigation, and even the brain. Research indicates that certain microtubules in neurons may maintain quantum coherence long enough to play a functional role in cognition, supporting theories like orchestrated objective reduction, (OR), proposed by Roger Penrose and Stuart Hameroff. If consciousness is linked to quantum processes in the brain, it could explain phenomena like intuition, creativity, and non-local awareness, bridging mind and matter at a fundamental level. Even in physics laboratories, experiments on quantum entanglement highlight the interconnectedness of particles in ways that defy classical locality. Entangled particles respond to measurements instantaneously, suggesting a non-local web of influence that may have profound implications for understanding consciousness. Some theorists propose that awareness itself could function as a non-local observer, interacting with the universe in ways that are subtle but measurable in quantum experiments. It is important to note that while these studies are compelling, they do not conclusively prove that human consciousness directly shapes reality. Many scientists caution that the effects observed are small and may have alternative explanations, such as environmental factors or statistical anomalies. Nonetheless, the accumulation of evidence, from interference patterns to REG experiments, entanglement, and quantum biology, suggests that the relationship between mind and matter deserves serious consideration. Together, these experiments challenge the classical assumption of an objective, observer-independent reality. They invite a radical possibility that consciousness may not merely perceive the universe but may participate in its unfolding, interacting with the quantum substrate from which all matter, energy, and experience emerge. While definitive proof remains elusive, the convergence of these findings points to a universe where mind and matter are deeply intertwined, a concept that resonates with both modern physics and ancient wisdom. Quantum physics does more than describe the microscopic behavior of particles. It challenges our most fundamental assumptions about reality, knowledge, and existence. If consciousness is linked to quantum processes, then the universe may not be a fixed, mechanical system but a dynamic, participatory reality shaped by observation. This realization has profound philosophical implications, touching on metaphysics, epistemology, and even ethics. One immediate consequence is the collapse of classical determinism. For centuries, Science operated under the assumption that the universe functions like a giant clock. If we knew all positions and velocities of all particles, we could predict the future with perfect accuracy. Quantum mechanics shatters this notion. Superposition, uncertainty, and entanglement reveal that at the fundamental level, reality is probabilistic. The idea that a particle state is only fixed when observed implies that the universe is not fully determined in advance. This challenges our conventional understanding of causality and suggests that potentiality, not certainty, lies at the core of existence. The observer effect also raises questions about the nature of consciousness itself. If awareness plays a role in collapsing quantum possibilities into actuality, then mind may not be merely a byproduct of brain activity. It may be ontologically primary, forming the basis of reality rather than emerging from it. Philosophers like Immanuel Kant proposed that our perception shapes experience. Quantum mechanics gives a scientific analog, suggesting that reality is co-constructed by observer and observed. This view blurs the boundary between subject and object, internal and external, mind and matter. The ethical implications of this perspective are equally profound. If consciousness participates in shaping reality, even in subtle ways, it implies a deep interconnectedness between all beings. Every action, thought, or intention could ripple through the quantum substrate of existence, influencing not just immediate outcomes but the broader web of reality. Such a view echoes ancient spiritual teachings about karma, responsibility, and the moral significance of awareness. It invites a sense of participatory stewardship, where our engagement with the world is more than superficial. It is integral to the unfolding of existence itself. Furthermore, quantum theory opens philosophical dialogue with mysticism and metaphysics. Concepts like non-locality, entanglement, and the holographic nature of reality resonate with centuries-old ideas found in Vedanta, Taoism, and Hermetic philosophy. These traditions describe the universe as a vibrational, interconnected whole, where consciousness is not merely observing the cosmos but is woven into its very fabric. Quantum mechanics does not validate mystical claims outright, but it provides a scientific language for understanding phenomena that classical materialism cannot fully explain. Ultimately, the philosophical implications of quantum consciousness demand humility and wonder. Reality may not be a fixed stage upon which events occur, but a dynamic interplay of potentiality and perception. The observer and the observed are inseparable participants in a living, participatory universe. This invites us to reconsider what it means to exist, to know, and to act, highlighting that consciousness may be both the lens and the brush with which the universe paints itself. Quantum mechanics transforms philosophy by suggesting that we are co-creators of reality, and that awareness, far from being a passive reflection, may be the most fundamental element of existence itself. One of the most profound philosophical interpretations emerging from quantum physics is the idea that the universe itself is a conscious entity, experiencing itself through the myriad forms it generates, including human awareness. This perspective reframes reality not as a lifeless mechanism governed by blind laws, but as a living, self-aware process, where consciousness is fundamental and matter emerges as a vehicle for its expression. The concept draws on the observation that quantum systems appear to require observation to collapse probabilities into definite outcomes. If observation, whether by a human or some form of awareness, participates in shaping reality, then consciousness cannot be incidental. It becomes integral to the unfolding of the cosmos. In this sense, every act of perception is not just a passive witnessing but an active participation in reality, a tiny thread in the universe's ongoing experience of itself. Philosophers and mystics have long articulated this view in metaphorical terms. In Vedanta, the universe is Brahman, infinite consciousness manifesting as everything we perceive. In Kabbalistic and Hermetic traditions, the cosmos is described as a living, intelligent unity, wherein every form reflects the divine mind. Quantum physics offers a modern analogy. The universe behaves not as a collection of isolated objects, but as a field of interrelated potentials, where all distinctions, self and other, observer and observed, are ultimately relational. The implications of seeing the universe as consciousness experiencing itself are transformative. It suggests that every entity, from the smallest particle to the largest galaxy, is a manifestation of the same underlying awareness. Human beings, then, are not separate from this process. We are localized expressions of universal consciousness, capable of reflecting on ourselves and, in doing so, allowing the cosmos to become self-aware. This idea resonates with the mystical notion that the universe knows itself through sentient beings. This perspective also reframes our understanding of time, causality, and reality itself. In a conscious universe, the classical notion of a fixed, linear timeline is replaced by a dynamic, participatory flow, where potential and actuality are intertwined. The quantum field becomes a canvas, and consciousness, whether planetary, human, or cosmic, acts as both painter and observer. Every moment, every perception, every choice contributes to the universe's ongoing self-realization. Moreover, the concept encourages a deep ethical and existential awareness. If the universe experiences itself through us, then our thoughts, actions, and intentions are not trivial. They are acts of co-creation within a living cosmos. Recognizing this interconnectedness fosters responsibility, empathy, and reverence for life, as each being is an essential aspect of the universe's conscious expression. While this view remains speculative and difficult to prove empirically, it offers a compelling synthesis of quantum physics, philosophy, and spirituality. It reframes consciousness not as a byproduct of matter but as the ground of reality, with the universe itself as the ultimate self-reflective observer. To see the universe as consciousness experiencing itself is to recognize that we are not separate spectators in a cold cosmos. Instead, we are conscious nodes within a vast, intelligent web, helping the universe to know, feel, and experience itself through the rich tapestry of existence. It is a vision of reality where mind and matter, observer and observed, self and cosmos, are inseparably intertwined in an eternal dance of awareness. The exploration of consciousness and quantum physics is exhilarating, but it is also fraught with misunderstandings, overinterpretations, and pseudoscience. While the possibility that mind interacts with the quantum world captures the imagination, it is crucial to approach these ideas with both curiosity and critical thinking. Skepticism and balance are essential to distinguish genuine scientific inquiry from fanciful claims that misuse the language of quantum mechanics. Quantum physics is inherently counterintuitive. Concepts such as superposition, entanglement, and wave function collapse challenge classical assumptions about reality, time, and causality. These features, however, are mathematical descriptions of subatomic behavior, verified through rigorous experimentation. They do not automatically validate metaphysical claims, such as the idea that humans can manifest physical reality simply by thinking about it. Such extrapolations often appear in New Age or self-help literature, where the term quantum is used metaphorically rather than scientifically. While these interpretations may inspire and motivate, they are not empirically grounded. At the same time, outright dismissal of the connection between consciousness and quantum phenomena risks throwing out potentially revolutionary insights. Experiments, such as those investigating the Double-Slit Experiment, quantum entanglement, or the effects of intention on random event generators, suggest that observation and interaction may play a subtle role in shaping outcomes. While the evidence is preliminary and often debated, it encourages a measured openness to possibilities without leaping to definitive conclusions. Maintaining balance means appreciating the profound mystery of quantum reality while respecting the boundaries of current science. Skeptical inquiry requires asking rigorous questions. Are results replicable? Could alternative explanations account for the phenomena? Are claims being exaggerated beyond what the data supports? Curiosity and imagination are valuable, but they must be tempered by critical reasoning to avoid conflating metaphor with physical law. Moreover, embracing skepticism does not preclude philosophical or spiritual reflection. Many interpretations of quantum mechanics, such as the participatory universe, the holographic model, or non-local interconnectedness, invite contemplation of the nature of consciousness, reality, and existence. Approaching these ideas thoughtfully allows us to explore the intersection of science and philosophy without succumbing to dogma or wishful thinking. The key is to adopt a dual perspective, grounded in evidence but open to wonder. Science provides methods to test, measure, and refine our understanding. Philosophy and contemplative practices offer frameworks to explore meaning, awareness, and interconnectedness. When combined, they create a balanced approach, one that honors the rigor of empirical inquiry while acknowledging the profound mysteries that quantum physics reveals. Skepticism and balance serve as a compass in the quantum landscape. They remind us that while the universe may be stranger, more interconnected, and more participatory than classical science imagined, our interpretations must remain anchored in careful reasoning, experimentation, and humility. By navigating between skepticism and openness, we can explore the potential interplay of consciousness and quantum reality with clarity, integrity, and wonder. Quantum physics has revealed a universe far stranger and more interconnected than classical science ever imagined. From the mysterious behavior of particles in the double-slit experiment to the instant correlations of entangled particles, the quantum world challenges our assumptions about reality, causality, and existence. Experiments suggest that observation, potentially consciousness itself, plays a role in shaping outcomes, blurring the line between observer and observed. Philosophically, this points to a cosmos in which mind and matter are inseparably intertwined, a participatory reality where awareness contributes to the unfolding of existence. Interpretations like the holographic universe or the universe as consciousness experiencing itself invite us to see reality as a living, dynamic interplay of potential and manifestation. While skepticism remains essential, embracing the mystery allows us to appreciate the universe as an eternal dance of mind and matter, where observation, intention, and consciousness are threads woven into the fabric of existence itself.